I'm going to spend now some time explaining how one particular non-parametric test, namely the Mann-Whitney U Test, works. This will give you a little bit of an idea of how these ranks are used and what is the mechanism. Again, it's a very superficial look at this test, but just to give you some idea about it. Okay. First of all, let me tell you that this test also goes by the name of Wilcoxon rank sum test. There is an interesting little story behind this, which I will not go into. However, just to suffice to say that Wilcoxon and Mann and Whitney came out with these two tests separately. And the two tests actually use different calculations. The number crunching is different according to whether you do one or the other. But then people realize that it doesn't matter what the number crunching is, their two approaches always lead to the same p-value. This is not a coincidence, it's a mathematical fact, and so they're really just equivalent tests. Okay. Now, what is the purpose of this test? This test really is asking whether a variable has the same average in two different groups. Okay. Now notice that I'm talking about average, not mean, because remember the mean is supposed to be applicable to numerical variables, but as soon as we start using these non-parametric tests, we have lost the numerical part. We're down to ordinal. So really I don't want to talk about the mean, but about average. Now if I don't want to talk about the mean, well, there may be that the desired null should be that the two populations have the same average, perhaps as the median, right? So this is really what we're after. Turns out actually that we need a slightly stronger null hypothesis. So the null hypothesis that this test actually requires that the two populations have the same distribution. So not just the same average, let's say the same median, but the same distribution. This is not a far-fetched or unusual thing, because remember, for instance, the t-test and ANOVA both require that the variability in all the samples being used have to be the same, right? So we are testing for the mean, but we're assuming that, well, if the mean is the same, everything else is the same, right? So in this case, because we're not saying anything about the variability, we have to make that a little bit clearer. Again, bit of a technical point, not a big deal, but just for you to remember in case someone mentions it. Notice also that this test is pretty much a non-parametric alternative to a two-sample t-test, right? We're comparing averages in two groups. If we could, we would use a two-sample t-test. But again, the idea is, well, we can't. And so what we're going to do is we're going to use this particular test. All right, so how does it work? First of all, we're going to assume only that the variable is ordered. So there is some kind of an order, so we can talk about ranks. Otherwise, we can't really do anything with it. All right. So what we're going to do is we're going to collect values from two samples. And for the sake of illustration, here is sample 1, here is sample 2. So we collected sample from the red population and from the blue population. Notice that those two sample sizes are different. That's okay. The Mann-Whitney U test can handle that. Okay. Now what we're going to do is we're going to combine all of these observations in one big group. Well, not that big, but that's because we're using small samples, and we're going to rank them within that one group. Okay, so what I'm going to do is I'm going to take all the values, okay, put them in order. I'm going to keep the red and the blue visually separate so I can tell which one belongs to which group. And then again, this is a non-parametric test, so I'm going to have to abandon the numbers and go just with the ranks. Okay, so we're going to figure out what the ranks are. We're going to rank them lower to higher. As I said, that's okay. Notice one little interesting thing. There are two observations which had exactly the same value. Okay, so both had value 8. Their ranks would have been 5 and 6, but because they're equal, we split the 5 and the 6 and we assign 5.5 to both of them. This is a standard procedure when we're dealing with ranks. If you have equal observations, they end up splitting the total rank. Okay. Now, what we're going to do next is we're going to compare the mean ranks, and here I do mean mean. Okay, so the usual average of adding up all the numbers and dividing by the number of observations, but this time we're going to do that for the ranks of the two samples. So here are our two samples, and we're going to compute the two mean ranks. So for the red one, we're going to add 1, 2, 5.5, 8, and 11. Divide by 5, we end up with a mean rank of 5.5. For the blue ones, we're going to add the 3, the 4, the 5.5, the 7, the 9, and 10. Divide by 6, we end up with 6.41. Okay, so those two numbers are different, but that's because they're coming from two different samples. Okay. Now, under the null hypothesis, remember, the null hypothesis says the two populations should have the same distribution. They should really be looking the same. Well, if they are the same, then the mean ranks should be roughly equal. But we know that random variability will generate things which are a little bit different. Okay, so what we're going to do is we're going to look at how different they are, with the idea that the more different they are, then the less likely it is that those two mean ranks were produced by chance alone, and therefore the smaller the p-value, and the more convinced we're going to be that the two populations actually come, the two samples come from from populations with different averages. Okay, so that's the basic idea. Again, let me give you just another illustration about that. So again, this fact that the more different the rank averages are, the lower the p-value. Actually, it should be mean ranks, because we are computing the mean, not just a general average. Okay, so let's say that the ranks fall like this. Again, red and blue denote the two samples, and so let's say that the observations from the red came in first, third, sixth, seventh, and 10th, and the other ones were the blue. If you actually compute the mean ranks, for the red turns out to be 5.4, for the blue 5.6. Well, they're very close, right? So this is what we would expect if the two populations were roughly the same. So they're pretty equivalent. We're going to end up with a large p-value. Now let's look at this situation. Now they're still mixed up, right? But you can tell here that the red ones are starting to go to the top of the heap, right? They start getting into the high position, the 9th and the 10th, and maybe even the 5th and the 6th, while the blue tend to be more on the lower side. If we compute the mean ranks, in fact, the red turns out to be 6.2, the blue 4.8. Now there's starting to be a more visible difference. So most likely the p is going to start getting smaller. Okay, is this significant or not? Well, we don't know yet, and I'm not going to tell you for this case. Okay, but certainly it's becoming smaller. And if we have something like this, you can definitely tell even by looking at it that the red ones are seem to be higher, seem to have a higher rank than the blue ones. In fact, if you compute the mean ranks, for the red is 7.8, for the blue is 3.2. So in this case, the p-value is going to end up being fairly small. Significantly small? We don't know. Again, I'm just giving you the basic ideas. There is a whole bunch of computations and number crunching and formulae that come into the computation of the p-value based on the Mann-Whitney U test. But we're not going to go there. Okay, so suffice it to say that this is the basic mechanism. You're comparing just the ranks of the two. The more they're different, the more they're an indication that the two populations are in fact different.